All right, we're going to look at the scalar product. Sometimes it's called the dot product or the inner product. And the way that it works is you take two vectors and you put a dot in between them. And sort of like similar to matrix multiplication, you multiply some things together and then add up all those separate products. So in 2 dimensions, if you had the vector 3, 5 dot product with 4, 1, you would multiply the 3 and the 4 together to get 12. You'd multiply the 1 and the 5 together to get 5 and add them together to get a dot product of 17. In 3 dimensions, if you had a dot product of 1, 2, 3, 4, 5, 6, like that, 1 times 4 is 4, 2 times 5 is 10, 3 times 6 is 18, and you would just add them together. And this is going to have some very cool results. Part of the reason it's called a scalar product is because you always get a single answer in the end. So I'd like you to try the next 2 examples. So if you write them as column vectors, there's the first one. Just multiply the components together and check your answer on that second one as well. So now we're doing new math with vectors. We have to go through and find out what are you allowed to do with vectors. Because we learned with matrices, if you multiply them and switch the order, you get different answers. So is the same thing true with the dot product for matrices? Well, no. You can do the dot product in either way, and it will be equal to each other. So whether you do u dot v or v dot u, it's the same thing. And if you're multiplying by another scalar in front, you can multiply that scalar first by u, or you could multiply that scalar first by v. Both of those would result in the same thing when you do the dot product. Part C there, if you're adding 2 vectors together in the brackets, well, you could distribute and do the dot product with distribution as well. And finally, if you have a 0 vector, anytime you do the dot product with the 0 vector, you will get 0 as well. Now, these are the interesting things that you can find out with the dot product or the scalar product. When you do the dot product of the same vector, the answer that you're going to get is going to be the same answer as if you squared the length of your vector. So let's take an example just to see that. If I took the vector 3, 4, can you see that the length of that vector would be 5? Because you would do a squared plus b squared equals c squared, and you would get 5. Now, if you do the dot product of this, you'll get 3 times 3, which is 3 squared, which is 9, 4 times 4, which is 16. And so you will get the same answer. It'll just be squared as a result, because you'll still get a squared plus b squared when you square it. Now, that's just a minor interesting thing. This is where things get really interesting. The dot product of any 2 vectors is always the length of the one vector times the length of the other vector times cos of the angle between them. So if we have 2 vectors, u and v, and they're joined like this. This would be the angle between them. And the dot product is always whatever the length of u is times the length of v times by cos of the angle in between them. Now, we're not going to go through a complete proof of why that happens right now, but with this, we can notice certain things really quickly. If u and v are perpendicular, in other words, if you have one vector this way and one vector this way, so that the angle between them is 90 degrees. Well, from our unit circle last year, we learned that cos of 90 degrees is equal to 0. And since u dot v is equal to the length of u times the length of v times cos of theta, and if this is equal to 0, that means u dot v has to equal 0 as well. What that allows us to do is the dot product is really easy to figure out because you're just multiplying corresponding elements and adding them up. It allows us to find out right away whether or not two vectors are perpendicular. Now, if the angle between them is between 0 and 90 degrees, or acute, so in other words, if this angle theta is between 0 and 90 degrees, well, then cos of theta would always be positive, because cos of theta between 0 and 90 degrees, quadrant 1 is always positive. So if your dot product is positive, then you know the angle between them is between 0 and 90 degrees. Similarly, as soon as your angle gets larger than 90 degrees, you know that cos of theta in quadrant 2 is always negative. And so if you get a dot product that's negative, you know the angle between them has to be bigger than 90 degrees. And probably the thing that we do most often with this formula is we rearrange it to get cos by itself, and now you can find the angle between any two vectors by just finding the dot product and dividing by the length of each vector. What's really powerful about this is it not only works in our two-dimensional vectors that we've done before, because in 2 dimensions, if you were told a length, this is 5 and this is 3, and you were given one other piece of information like 7 here, and you wanted to find that angle, you'd use your cosine law. Well, the dot product does that sort of same thing, just uses its lengths, and it makes the calculations actually quite a bit easier than if you were going back to your cosine law. So let's do one with 3 dimensions. You've got the vector v, 3, 2, and 1, and w, and we want to find the angle between them. So the first thing we'll do is we'll write out our formula. And then we'll calculate each thing separately. So if we multiply our corresponding elements, we'll get 12 plus a negative 2 plus 2. And if we find the length of v, 3 squared plus 2 squared plus 1 squared, that'll be the square root of 14. 4 squared plus negative 1 squared plus 2 squared, will be the square root of 21. And so if we simplify this, we have 12 over the square root of 294. Or you could have written that as 7 root 6. So then to find the angle, just go to your calculator and do cos inverse of that. And you can either have your calculator in radians or degrees. And you've got 45.6 degrees. So what did we just do? Okay. To get a picture of this, you have a vector that goes 3 in the x direction, 2 in the y direction, and 1 up. One, two, 3 in the x direction, 2 in the y direction, and 1 up. That would be that vector. And then we have another vector that goes 4 in the x direction, -1 in the y direction, and then 2 up. And we just found that angle between them. Now, if someone had just drawn that picture and asked you to find that angle, that would be quite complicated. But using this formula and this concept actually makes it quite easy. I'm going to learn some new fancy words. Orthogonal. It's just another fancy word for perpendicular. I don't know. So there's a lot of vector questions that use perpendicular or orthogonal because they want to trigger you. So whenever you see either of these two words, they want to trigger you to think, well, I know that the dot product should equal 0. Because if my dot product's equal to 0, then cos has to be, the angle has to be 90 degrees because cos of 90 is equal to 0. If that's the case, here's our two vectors, 2m, m, and 8. And our other vector is 1, 3m, and -1. The dot product of these has to equal 0. If you multiply corresponding elements together and add them together, we have a quadratic which we can factor. It would have to be 3m and m in order to get 8, but still have the outside and inside get 2. 2 here, 4 here, outside is 6, inside is 4. Make my outside positive, inside negative. And so we get two values for m. So here we have the vector 4, negative 3. Any vector that is parallel to that would have the same slope. And in order for it to have the same slope, well, 4, negative 3, if we think about that, that's going over 4 this way, down 3. In fact, when you think of it with slopes, can you see that the slope would be negative 3 over 4? And any vector that is in that direction, bigger or smaller, will be parallel to it. So you can take your vector 4, negative 3 and multiply it by anything, and you would get an answer that's parallel to you. So what would you like k to be? Pick your favorite number. 21? So if you picked 21 for k, you'd have 84 and negative 63 as a possible answer for something parallel to you. Anything would be fine. In order to pick something that's not parallel to you, you just have to make sure that you choose something that isn't a multiple of 4 and negative 3. Chances are if you just guess two numbers, you would get it right. But then you're living on the edge a little bit. I mean, what you could do is just keep one the same and then change the other one. And if you think about that, can you see that 4, 5 would be a vector up there? For sure wouldn't be parallel to 4, negative 3. Now to get something perpendicular or orthogonal to you, okay, we know that the dot product would have to equal 0. In this case, we could also think about, well, what do you know about perpendicular slopes from the math you took in grade 10? What's the slope? If I wanted to find something perpendicular to the line that had a slope of negative 3 over 4, its slope would be 4 over 3, right? We used to say the negative reciprocal, or in French, I don't know what you would have said in French, but you flip it and make it negative, right? So if our slope has to be 4, 3, you might be able to just say, well, if slope is 4 over 3, that means my rise is 4, my run is 3. If you were thinking about multiplying things together with the dot product to make it equal to 0, and we knew that our first one was 4 and negative 3, you need to put something in that second one so that they cancel out. Does it make sense that if I multiply by the opposite numbers here, they'll both be 12s? And as long as your sign is different from where you began, one will be positive, one will be negative. So if your original one that you had both positive numbers, then you'd have to put a negative somewhere in the second one. So for example, just as another example here, if I wanted to find something orthogonal to 3, 7, I would need 7 and 3, and I could choose to put the negative there or with the 3. It wouldn't matter where that negative was, because then you would get 21 and negative 21, and they'd cancel out. Now, as soon as you move to vectors 3 dimensions, it gets a little bit trickier, because you have to figure out something that would go together with all of them. Any suggestions? You want to put a 1 here? And then 5 and then a 3? No, I don't think that's going to make 0. 5 in front of the 3. I mean, there's a bunch of different answers. There's more than one right answer. Okay? A 1 with a 5. 5 under here? And then a negative somewhere.
-1 and a -5 under.
Oh, okay. You want the -1 or -5? 15 minus 5 minus 10? Yep, that'll work. So it wouldn't take too long to find one that's orthogonal with a 3 by 3. I mean, if you want to do, you want to make your life easier? I don't want to worry about that bottom one, because then I can just go 5 and 3 and make one of these negative. But maybe that makes it too easy. So here we have two vectors, and we want to find x if they're parallel, and we want to find x if they're perpendicular. So I'll let you try that. All right, how did you do? If they are parallel, so W is 1 and -3, and V is 2 and x. If they're parallel, then V has to equal something times W. Does that make sense? What would K have to be if we have a 2 up here? K would have to be 2. So then x, if K is 2, would have to be -6. So the idea, if two things are parallel, you know that one is a multiple of the other one. So I have the vector W. I know it's 1, -3. I can put a K in front to say I know that vector V, if it's parallel, is some multiple of that. And then we get a simple equation that K times 1 has to equal 2, so K would have to be 2. If they're perpendicular, then you know that the dot product has to equal 0. So we know that vector V is 2 and x, and vector W is 1 and -3, and that has to equal 0. Well, if we multiply this out, we get 2 plus -3x equals 0, and solving for x, we'd get 2/3.